Good afternoon. Welcome to the IIS Discovery Science Seminar. The seminar was organized by IIS NTU in collaboration with graduate student clubs of SBS, MAE, and LKC. On behalf of IIS, I welcome Professor Paulo Bartolo to this seminar. Thank you so much for taking the time for it.
Thank you.
Before we begin, I would like to introduce Professor Paulo Bartolo. Professor Paulo Bartolo got his PhD degree in polymer physics from the University of Reading in the UK. He is the former chair professor on the advanced manufacturing at the University of Manchester and the founding director of the Center for Rapid and Sustainable Product Development in the Polytechnic Institute of Leiria in Portugal. He also has been advisor and reviewer for several global funding agencies, such as European Research Council, Engineering and Physical Sciences Research Council, and Medical Research Council. In 2021, Professor Paulo Bartolo joined NTU as director of Singapore Center for 3D Printing. Professor Paulo Bartolo is considered by Microsoft Academic as the most salient author worldwide in the biomanufacturing field, and recognized as one of the top 2% scientists in the world by Stanford University and Elsevier. He was awarded the 2022 Medal of Merit by the city of Leiria for his national and international achievements. So I welcome Professor Paulo Bartolo to present a seminar on can 3D printing print cells in our body.
Thank you very much. I have this. So can we switch now? Well, good afternoon. It's thank you very much for the invitation to be here. The most interesting part of being a professor is to be able to spend some time with students. So thank you also for coming. And during the next 1 hour, we will try to answer this question: can 3D printing print cells directly into our body? But we are going to do this, or to answer this question, through a kind of journey, showing step by step different areas where additive manufacturing is being used for medical and biomedical applications, till we reach the answer or potential answer to this question. Well, but before we start, because this talk will be about biology and 3D printing, it is important to know if you know what is 3D printing. Who knows or who don't know what is 3D printing or additive manufacturing? Okay, so this is a good point. So you know that 3D printing describes a group of technologies that create objects layer by layer, similar to nature. So nature also creates structures layer by layer. And one example is a tree. So the tree grows by this deposition of cellulosic material, ring after ring after ring. And this is what we are doing when we use a 3D printing machine. The second, and we are talking about 3D printing, the second question that I would like to ask you is if you are aware of the Singapore Center for 3D Printing, because most of the work that I'm going to present today have been developed at the Singapore Center for 3D Printing. So who doesn't know about the existence of this center? One. So we need to invite you to visit the center. 2, 3, 4, 5, 6. So several never heard about the center. So we need to organize a visit for you to see the center, because the center is, as you can see from these photos, here in the arc. So we are occupying the B4 and the B3 floors. So we will be more than happy to show you the facilities and the different labs that we have here at NTU. So the Singapore Center for 3D Printing is a research center focusing on 3D printing and cover all aspects related to 3D printing. We are doing design for 3D printing, because designing a part to be 3D printed is totally different than designing a part for conventional manufacturing. We develop materials. We develop new systems, 3D printing systems, or optimize existing systems. We do modeling and simulation. And our activities are organized around different industrial sectors. And what is relevant for today is this pillar, biomanufacturing, where we are using additive manufacturing, mainly for the fabrication of medical devices, biosensors, for tissue engineering and regenerative medicine applications, and also for food printing. So throughout this journey that will be my talk with you, I will start by talking about the use of additive manufacturing to create medical devices. This is the first step. And then I will move to tissue engineering and regenerative medicine, focusing initially on strategies to repair, to regenerate tissues. And finally, we will talk about bioprinting to see if we can answer the question, can 3D printing print cells directly into the body? So you see that in terms of areas, the center covers almost all major industrial sectors in Singapore. We have a wide range of machines. And let me give you some examples of products that we are creating at the center. You probably know about this concept of smart materials. So materials that can change their shape or properties or colors in response to environmental changes like temperature, humidity, light, pH, whatever. So this is an example of a 3D printed smart structure. So this is a smart gripper changing its shape as a function of temperature changes. And we are taking the advantage of this characteristic to move one object from one position to another position. Another example, in this case more artistic, is this butterfly moving the wings, again in response to changes in the temperature in the media. So smart materials is one area of activities at the center. We are using also 3D printing to print electronics, flexible electronics, transparent electronics. We have capabilities to print complex PCB structures, three-dimensional antennas for 5G, 6G, and also devices like a radio. So this was developed by one of our engineers, and he used different additive manufacturing techniques to print what we believe is the first 3D printed radio, not fully 3D printed, but a large number of components 3D printed. So we use a powder bed fusion machine to print the cage, and then other 3D printing systems to print the different electronic components. And the radio is working, as you can see here.
Okay.
Not the best noise, not the Pioneer or Sony or whatever, but at least we can listen some music, and we hope to improve this in the future. We are using 3D printing to print large objects. Professor Tekneng is here. He's responsible for our building and construction program. And this was something that it's a kind of iconic product at the center, this 3D printed bathroom, printed in 9 hours. So what he's mentioning here, it's not the final time after optimization. And this printed bathroom, which you can see at the center, was licensed to a company in Singapore for commercialization. We can print drones. We can combine techniques to print the drone and also to print these conductive traces on top of the cages of drones. This is a new capability that we will have very, very soon, which will allow us to print large plastic and composite parts. It's a partnership with a company from Japan. And they printed this ball share for us to showcase in an exhibition that will start next week in Japan. And someone mentioned what will be the next trends in terms of FDM. This is an example. So in this case, we don't use filaments. We are using pellets. But we are able to create very large parts. We can print different materials. We can create functional graded structures using these extrusion-based systems. And other examples of objects that can be 3D printed at a center. Now, and this is from a movie called The Fifth Element. What we will start doing is to answer these questions. Can we use 3D printing to repair and regenerate damaged tissues or organs? Can we print tissues or organs? And finally, can we print in the human body? Before that, let's start with the basics. Can we print medical devices? And the answer is yes. So I'm a mechanical engineer, but I was really fascinated by medicine. Before being an engineer, my dream was to be a medical doctor. But for different reasons, I started a mechanical engineering degree. And I'm very happy to be a mechanical engineer, but I'm fascinated by medicine. And I had the opportunity many, many years ago to link both passions, additive manufacturing and medicine. So many years ago, this was around 2008, I guess, I was in Portugal, and we created a network that we call it as biofab for biofabrication, so the use of additive manufacturing for medical applications, comprising partners, universities, and hospitals from different regions in Iberia, so Portugal and Spain, and America, Central America, Cuba, Mexico, and South America, Venezuela, Brazil, and Argentina. And the idea was to explore the existing technologies in these countries, to develop new technologies if possible, and to use natural resources to create medical devices. Let me show you some examples. This was one of the first cases that we solved in partnership with clinicians from a region in Brazil called Pernambuco. So this was to address this problem. So these patients suffer very significant frontotemporal lesion. And based on medical data, we use 3D printing in this case to print a mold. And then we cast a PMMA, polymethyl methacrylate material to create an hollow prosthesis for the person. Another example that we conducted as part of the BioFab network was this one. In this case, in partnership with Hospital de Clínicas in São Paulo. And this was to create a cranioplasty for a young boy. And the problem that we were facing was, okay, the boy will grow, and we need to keep this in mind, because otherwise, if we design the prosthesis for him now, in a couple of years, it will be necessary to remove the implant and to create a new one. So we design an adaptive prosthesis with a kind of sliding mechanism that was able to expand following the growing process of the kid. And other examples where we combine different additive manufacturing techniques to create, for example, biomodels and the implant. And this allowed the surgeons to plan the surgery, to validate the implant using these different models, biomodels, and the implant. So this is the beginning. So this was our first step in terms of the use of 3D printing for medical applications. We are doing the same also here. And we start a partnership with Singapore General Hospital. We are going to formally sign the research collaboration agreement with them. But again, we are using additive manufacturing to address different cases they are presenting to us. One was this ankle-foot orthosis that we printed for a patient suffering from a specific type of diabetes, so he was not able to have some movements in the lower part of the leg. The AFO was designed to have mechanical stability, but also to be lightweight. Another example was this printed model showing a very big bone cancer zone, and this was for the surgeon to plan the surgical intervention. And a few other examples, these scoliosis brace, this knee brace for an elderly patient. So these are examples of projects conducted at a center addressing clinical needs. And all of these projects are being developed by students, and it is good to show the faces of the student behind the projects, and this is the case of the scoliosis. So this was the first step. So the exploration of additive manufacturing to print different types of prosthetic devices. So after that, we move into a different field. And that field was about the use of additive manufacturing, the same machines that we were using for other applications, but with different materials, biocompatible and biodegradable materials. trying to do repair or regeneration. And most of the slides that I'm going to show you are related to this. So the use of 3D printing for tissue engineering applications. Let me show you our video about 3D bioprinting that
3D
introduces the
bioprinting
problem,
is a revolutionary technology
and I will give you
that has
several
the potential
examples
to
about
change the
this.
way we think about medicine and biomedical research. It involves using 3D printing technologies to create living tissues and organs that can be used for tissue engineering and disease modeling applications. As the worldwide population ages, new therapies are required to help support a healthy and vibrant old age and reduce the strain and cost on healthcare systems. Due to the crisis in tissue and organ transplantation, every year, thousands of people die whilst on waiting lists, which could be prevented. In the meanwhile, children with defects in tissues and organs can require multiple surgeries as they grow up, which is physically and emotionally distressing as there is no therapy that can grow with them. One of the most exciting things about bioprinting is the potential to help solve these problems by creating tissues and organs on demand using the patient's own cells. The process of bioprinting involves creating a digital model of the tissue or organ that needs to be printed. This model is then loaded into a bioprinter, which uses specialized bioinks that can be made entirely of living cells or with other biomaterials to print the tissue or organ layer by layer. To develop functional tissues and organs that can actually be transplanted into a patient, then numerous hurdles need to be overcome. These include the vascularization of large tissues so they don't die from oxygen and nutrient starvation. To achieve this, the common tapered print head can be replaced with the coaxial print head, which prints multiple materials in a core and shell structure, while the core material involves the use of sacrificial material, which can be removed later to create the hollow structure. Bioprinting can also be used to fabricate in vitro models that offer the possibility of drug delivery tests, disease development studies, thus enabling the creation of patient-specific histopathological models and corresponding personalized treatment protocols. As such, it can be seen that the possibilities of bioprinting are exciting and offer great potential for solving many healthcare-related problems in the next few decades.
So, after the first phase, using 3D printing to create prosthetic devices, we move to this new area, using 3D printing combined with biocompatible, biodegradable materials, cells, growth factors, to create constructs for tissue repair and tissue regeneration. And we are using additive manufacturing mainly for two main approaches. One is this scaffold-based approach, where we use additive manufacturing to create three-dimensional porous structures, biocompatible and biodegradable porous structures, that serves as a support for cells to attach, proliferate, differentiate, and create a new tissue. And basically, the concept is shown in this video. So imagine a person suffering from a bone defect. We print a scaffold with characteristics similar to the bone tissue. The defect zone is occupied by the scaffold. The scaffold will recruit cells from the surrounding tissue. The cells will grow on top of the scaffold. They will create a new bone tissue, and during this process, the scaffold will disappear. So by the end, we have a new tissue in the space that was initially occupied by our scaffold. So this is the concept. The second approach is this cell-laden approach. And this is slightly different because in this case, we use different additive manufacturing technologies to print bioinks, so aerogels containing cells. An example is shown here. So imagine this patient suffering from osteochondral defect. So again, based on medical information, we use this medical information to create a construct, a three-dimensional model of the construct. And then we use additive manufacturing to print such construct using bioinks containing cells from the patient. In the case of an osteochondral defect, we need to combine technologies, and I will show you this later, because we need to have one zone corresponding to bone and then the different zones associated with cartilage. But the critical element here are these bioinks, so hydrogels containing different types of cells. And we are using, in fact, different types of cells. So most of the work, or in most cases, we are using stem cells, so cells that can be differentiated into different types of cells, but we are also using differentiated cells. Let me start with the first one, the scaffold-based approach. These are examples of scaffolds that we printed. These are PCl graphene scaffolds, so a combination of non-conductive polymers and conductive materials. We developed these to create electroactive scaffolds, and I will show you a slide where we demonstrated that by combining these scaffolds with an external electrical stimulation, we accelerate bond regeneration. This is a different type of scaffold, so in this case it's a scaffold made with a polymer, bioceramic, containing alendronate. And this scaffold was designed for patients suffering from osteoporosis. And it was a scaffold that was designed to, with two main aims. One was to treat the problem, the other one was to induce regeneration. Well, in the scaffold-based approach, these are usually the main steps. So we create a scaffold. We can directly implant the scaffold into the defect zone, or we can seed the scaffold with cells, pre-culture in a bioreactor, and then implant it. Similar to any other structure, so for example, when we design and produce a mold to create a plastic bottle, there are lots of things that we need to take into consideration. The same is applicable here. So we need to consider different aspects to design a scaffold. And the first one is a combination of mechanical properties and degradability. So if you remember the first movie that I show you, the scaffold is designed to fill the lesion. And throughout time, the scaffold will degrade, and the space that was occupied by the scaffold will be occupied by the new tissue. So this is one of the first challenges that we have. It is how to match the degradation of the scaffold and the regeneration process. The second is the mechanical properties. So initially, the space is only occupied by the scaffold, so the scaffold should support all the physiological loads. And then gradually those loads will be transferred to the new tissue being formed. So this is the first challenge and the first aspect that we need to consider when we design a scaffold. The second is that these scaffolds, which must be porous structures, they must present full pore interconnectivity. And again, this is why additive manufacturing is the ideal technology to create these structures. The second is related to some surface characteristics of the material. So most of the polymers that we are using to create these scaffolds are hydrophobic materials, and cells don't like hydrophobic regions. So there are different methods to solve that. For example, using plasma treatment or chemical elements. And an example is shown here. So we printed a PCl scaffold. And as you can see, the PCl scaffold is hydrophobic. And the same scaffold, same material treated, shows an hydrophilic behavior. So by modifying the surface properties of the scaffold, we change a key characteristic to promote cell attachment and proliferation. But nevertheless, this poses some problems. So when we move from an hydrophobic scaffold to an hydrophilic scaffold, what's happened is essentially the number of cells that attach to the scaffold, it's much higher in the case of an hydrophilic scaffold. And what we observed was by treating the initial scaffold, the PCl scaffold, using a plasma treatment, for example, what we observed was that a large number of cells were attaching and growing, blocking the pores. As you can see here, the cells are bridging. So this is a filament of the scaffold, and these are stem cells, and they are bridging the filaments. And after a certain period of time, they block the pores. And because of this, it was not possible to supply oxygen and nutrients in the cells inside the scaffold. And this is vital because the aim is to create a three-dimensional tissue. So to address this problem, and that is the advantage of being mechanical engineers, we decided to create a new machine. And my group, and especially in my case, I was forced since the beginning to develop machines because as he mentioned, I started my career in Portugal at the Polytechnic Institute of Leiria. And when I started my career, we had no money to buy very expensive machines. So we were forced to develop our own machines. And I'm going to show you the first machine that we use in a couple of slides. So to address this problem, we developed a machine that we call it as, that it was an hybrid machine. And this machine combined an extrusion system. In fact, we were able to print three different materials. We have a screw printing head and pressure-assisted printing heads. So using this printing head, it was possible to print three different materials in one layer. And a plasma system. And with this plasma system, it was possible to do surface modification layer by layer in a selective way. And our aim was basically to do this. So instead of the traditional approach, which was printing an hydrophobic scaffold, do plasma treatment, our idea, and as you saw, that approach didn't solve our problem. So our idea was to have this machine to print one layer of an hydrophobic material, use the plasma jet to create an hydrophilic region at the center, and repeat the process layer by layer. And then because cells are able to sense the environment, when we see the cells on the scaffold, the aim was to force the cells to migrate to the internal zones of the scaffold, growing from the internal zones to the outside. So this was the idea behind this machine. Again, we need to have a large number of cells attaching to the scaffold. So we develop other methods to do that by modifying the surface characteristics of our scaffold One example is shown here. So we printed the scaffold, submitted the scaffold to an acetone vapor annealing. And basically by doing this, what we have done was to induce a kind of recrystallization process. So we remove the amorphous regions at the surface of the filament, and we induce the formation of new crystal zones on top of the existing crystal zones, creating a certain roughness in a more or less controlled way at the surface of the filaments. And then we doped also with dopamine to improve the biological properties. We explore other strategies, such as, for example, coating the scaffold with silica nanoparticles, again to induce roughness in the filaments to increase cell attachment. And we were able to obtain what I think very nice and very artistic images, and I'm going to show you two. So again, this is a scaffold. As far as I remember, this is a scaffold, PCl scaffold containing graphene, seeded with steam cells, and you see the cells breaching the two filaments. These are preosteoblasts. So we seeded the scaffold with steam cells, induce osteogenic differentiation, and you see the preosteoblasts and the beginning of a pre-mineralization process. Well, I mentioned a couple of things that we need to take into account when we design the scaffolds, mechanical properties, surface characteristics. The architecture of the scaffold is also important. So if we keep the same porosity, but if we change the architecture of the scaffold, so the angle between the filaments, we change the mechanical properties. So the design has a direct impact on the mechanical properties. But the design has also a direct impact on the biological behavior of the scaffold. And you can see this here. So we produce scaffolds with different pore sizes, so different distance between each filament. And as you can expect, by decreasing the filament distance, and this should be till a critical value, we increase the cell proliferation because it's easier for cells to breach, cross the pores. But if you remember the video, vascularization is an issue that we need to consider when we design these scaffolds. So it is important to have large pores to promote vascularization. So this is not an ideal situation. So we decided, okay, so let's keep the pore size, but change the architecture. And by the way, all of these scaffolds were printed using this 090 laydown pattern. So if we keep the same pore size, but if we change the architecture, we change the biological performance of the scaffold, changing essentially the surface area. So the architecture of the scaffold is a parameter that we need to take into consideration. And the fabrication process also. So this was something recent. So we printed scaffolds, composite scaffolds, PCl and TCP, tricalcium phosphate. Same geometrical characteristics, architecture, pore size, filament diameter, but we use two different printing methods. In one case, we use melt printing. In the second case, we use dichloromethane to create an ink, and we use a solvent printing approach. So by the end, we obtained the same scaffolds, but scaffolds with different morphological characteristics. Crystallinity was different, surface roughness was different, mechanical hardness, surface hardness was different, and because of that, we observe a different cell behavior. So the technique is also important. So this means that designing such kind of structures, even before implanting the cells or seeding the cells, it's quite a challenge. Where we also develop different strategies to create more biomimetic structures. One example is shown here. So we try to create scaffolds with printed filaments mimicking the structure of bone. And the idea was to mimic these structures. So in the bone we have collagen fibers in between a ceramic matrix, an hydroxyapatite matrix. To create these, we mix PCl, hydroxyapatite, and multi-wall carbon nanotubes. During the printing process, the multi-wall carbon nanotubes were aligned according to the printing direction, and we were able to replicate this kind of structure. So a kind of biomimetic scaffold, even changing, but of course with different materials. We didn't use collagen materials in this case. The other idea was to create more hierarchical structures. So in this case, we use an extrusion system and an electrospinning. The extrusion process was used to create the scaffolds with large pores to promote vascularization. But to promote cell proliferation, we use an electrospinning system to create a nano-scale mesh. You can see very small fibers on the top of the scaffold. We use a rotational collector, so we create some cavities on this collector. We position the collector behind the extruder to create the first layers of the scaffold, and then we induce rotational movement on the collector, and we use the electrospinning. And by using this rotational of the collector, we obtain a very aligned distribution of fibers. Other strategies, and knowing that bone has piezoelectric and reverse piezoelectric properties, we decided to create electroactive scaffolds. We are now focusing on piezoelectric scaffolds, but a few years ago we decided to develop piezoelectric scaffolds using, initially we use a combination of a non-conductive polymer and a conductive polymer. We use polyaniline, but the results were not good. So we decided to replace the conductive polymer using carbon nanotubes and graphene. And basically the strategy was to create such scaffolds and to see what was the result when we combine such electroactive scaffolds with an external electrical stimulation process. And we tested this in rats. We created a critical size Calvaria defect in the rats. We compare the regeneration process without the use of any scaffold, non-conductive scaffolds, electroactive scaffolds, and in all cases with and without electrical stimulation. And what we observed was, in all cases, multi-wall, graphene, in all cases was that the combination of electroactive scaffolds and electrical stimulation accelerates angiogenesis, accelerates mineralization, and allows us to obtain a more organized new bone. We spend lots of time determining the critical value of graphene and graphene oxide, multi-wall carbon nanotubes to avoid any toxicity. But then we decided to do something different. So we realized that below a threshold value, the presence of graphene or multi-wall carbon nanotubes of graphene oxide or whatever were not or didn't present any toxicity, allow us to increase the mechanical properties of the scaffolds and to improve the biological performance. if we use concentrations higher than that critical value, we observe some toxicity. So we decided to take advantage of this to create dual functional scaffolds. And the idea was to use these dual functional scaffolds for bone cancer applications. So in bone cancer, you know that tumor resection is the clinical approach. But even if we remove a large size of the bone, larger than the tumor size, it is difficult to eliminate all cancer cells. So to address this, we decided to create this dual layer and dual functional scaffold. Basically, the first layers were made using biocompatible and biodegradable scaffold, but containing high levels of graphene or graphene oxide. Those high levels of graphene and graphene oxide generated a significant high level of reactive oxygen species, which induce oxidative stress. And we realized that healthy cells were less sensitive to the levels of oxidative stress that we induce compared to cancer cells. So we induced the death of cancer cells without any significant effects on healthy cells. So that was the idea of the external layers. After this effect, the middle region was made with the same polymer, but containing relatively low levels of graphene or graphene oxide, and the aim was to recruit healthy cells and to stimulate the regeneration process. So this was the idea. Again, many years, few years ago, this was probably in 2015 or 2016, I have good friends in Turkey, and one year I went to Turkey, and I was surprised. I had discussions with colleagues from university in Istanbul, and I met some clinicians in Istanbul, and I was impressed with the problem they told me associated with the Syrian civil war. So lots of Syrian refugees went to Turkey. A significant number of those Syrian refugees had significant bone problems due to explosions. And the problem that the doctors were facing was the high number of amputations, because in the majority of the cases, the patients had very severe bone problems and very infected lesions. So amputation was the common strategy, with lots of problems associated with such a clinical approach. So we decided to submit a project to the UK, the EPSRC, to solve this problem. So basically the idea was to create a different type of scaffold, so different from the scaffolds that I showed you before, with a structure, a topology similar to bone, so anatomically designed scaffolds, with materials allowing us to achieve properties similar to bone, in different shapes, easy for the surgeons to assemble in the hospital, creating a new bone. And that's why we call these structures as bone bricks. So element by element, it was possible the clinician to create a new bone to fill these big gaps, avoiding amputation. So to do that, it was necessary to create new toolpath strategies. We program a lot to create these anatomically designed scaffolds. These all structures, initially the idea was to use a metallic nail, but Later, we decided that it was not necessary, and basically the idea was to use a calcium sulfate paste with antibiotics to avoid any infection. But we designed these anatomically designed scaffolds with a gradient of pore sizes. We tested different architectures, different material combinations, and finally we achieved the right architecture, the right material composition, and I think that the next image shows lots of blood, so I'm very sorry for it. No, not this. So we created, as I mentioned, these functional graded structures. Those structures were able also to control the behavior of cells, direction of growth, cell density, and we started some preclinical studies inducing very large bone defects in sheep. This was never tried before. Such kind of defect was never tried before. So we are still in this preclinical validation of our bone bricks. So this was, let's say, the second phase. So initially we started with 3D printing to create prosthetic devices. Then we used 3D printing to create these scaffolds, which can be described as molds to give shape to cells to create a new tissue. I forgot to mention this. So in all of these cases, in all of our work, we need to do animal studies. These are expensive, time-consuming, and there are also some ethical issues because we are testing these in animals. To avoid that, we are using machine learning to create an in silico animal model based on histological images, and basically the idea is to be able to predict the long-term behavior of scaffolds and to design scaffolds in terms of architecture and material composition to achieve a specific performance. So I mentioned that when I started the work, we had no money to buy expensive machines, so we started with this machine, the bio extruder. So this was the work of one MSc student and one PhD student. So they developed everything, the hardware, software. This was a pellet-based material. Later, for a company, we developed a fully integrated machine with different zones. And this machine, we call it BioCell, was a machine allowing to print a scaffold, do sterilization, cell seeding, and the final stage was a bioreactor. Now, after this, we start moving for the concept of bioprinting. So using 3D printing to print aerogels containing cells. Recently, we signed an agreement with CellLink. So most of the activities in partnership with CellLink here at the center are related to 3D bioprinting, focusing on different applications. So in this case, the critical aspect is related to the design of the bioink, the design of the hydrogel used to encapsulate cells. And there are different aspects that we need to consider. We need also to focus on the right cross-linking mechanism to guarantee that we achieve a construct with good properties and also good behavior for the encapsulated cells. With 3D printing, we can use different types of aerogels containing different types of cells, allowing us to create very complex structures that can be then implanted. So this is an example of a bioprinting system printing different materials. We can do even more complex structures, and this is something that some of our students, and there are a few here, are exploring, which is instead of using additive manufacturing to create structures layer by layer, is to use 3D printing to create free-form structures without this layer-by-layer process. And to do that, basically what we have is a support media, and we write inside the support media. And by the end, we can keep the support media, depending on the applications, or we can remove the support media using only what we printed inside. So we can print very complex structures. We can print different materials, in this case, different hydrogels containing different cells. And this is, let's say, the preliminary step for, not now, but in the future, to create more complex tissues and the beginning of potentially printing organs. We are combining technologies. One example is shown here. This is an osteochondral defect. So we need to print one zone corresponding to bone using hard materials, so PCL and TCP. And then on top of this, we use bioprinting to print inks containing cells. Most of our work in this area is focusing on two main tissues. One is skin, and the other one is cartilage. Let me briefly mention some of our work related to skin. So we spent a few years developing a proper bio-ink to create skin. And our bio-ink is based on pectin. Pectin is a plant-based material, a terrible material because it is not, doesn't provide any biological cues. But because of that, we decided to use it because it is a good material to tailor. So initially, we use a free radical polymerization process. So we functionize the material with metacrylate. We use a dual cross-linking approach. So basically, we induce ionic cross-linking using calcium chloride. And basically, the idea was to increase the viscosity, guaranteeing good printability, good shape fidelity once we print it. And after printed, we radiate with UV to create a final construct. And the first steps were conducted using only fibroblasts. So the results were quite positive. After 14 days post-printing, cells were alive. They were creating networks. They were producing proteins, generating their own extracellular matrix. These are some confocal images, 3D reconstruction confocal images showing cell spreading. And this shows cell spreading surrounded by the ECM structure. But we were not happy with the chemistry. And we were not happy with the chemistry because we used a simple chain growth mechanism, lots of limitations. And one basic limitation was that the cross-link structure was quite rigid. Rigid in terms of we kept the internal free volume more or less constant during a large period of time, not providing additional space for cells to grow. So we decided to change the chemistry from a chain growth mechanism to a strap grow mechanism using click chemistry. We added also degradable peptides, and basically the idea of using these degradable peptides was to increase the internal free volume to create more space for cells to grow inside. And after optimizing the ink, we printed, and this was the strategy. So we printed the first layers of the ink containing fibroblasts, submerged to a culture media, printed the keratinocytes, submerged to culture media, and then we exposed the upper face to air to induce stratification. And the results were pretty good, as you can see here from the histological images. Structure similar to human skin, similar properties, similar cellular organization. We are increasing now the complexity of such structures. But what is interesting from a 3D bioprinting is that instead of printing these materials in the lab, we can print those materials directly into the body. This is a very simple example where we are printing the bioinks on top of a defect in a rat. So can we use 3D printing to print cells directly into the body? The answer is yes. And this was something that we decided to develop many years ago, and we have been investing a lot because our aim is to be able to develop a machine like this, a machine combining, and again, this is a mechanical engineering driven idea. So using scanning systems to scan the body of the patient, determining damaged lesions, using that information to create three-dimensional models of the constructs that we are going to print, and then using bioprinting to print these different materials and cells directly into the body. This was not developed by us, but it's a similar idea. In this case, the printing head is quite large, covering a large area, and this is something being developed by colleagues at University of Toronto in Canada. Printing skin directly into the body, covering very large skin-defected regions. So we are interested in skin. We are also interested in cartilage. Cartilage is something that we are focusing on the materials now, developing these materials. But let me give you some examples of strategies to print cells directly into the body, in this case to treat or to address cartilage issues. So this is an example using magnetic micro robots, biodegradable robots containing cells. These robots are introduced into the defect zone using these needles, and then a device with a magnet is used by using magnetic forces to orient and to control the position of these micro robots that deliver the cells, inducing regeneration. We can use complex systems, but also very or relatively simple systems like handheld devices. And this is an example of such device. So a kind of syringe system with two reservoirs containing different materials and a UV source for curing, being used again to treat defects in the knee. Finally, we are also addressing another problem that we have in this area. So, except cartilage, all of the other tissues are vascularized tissues. So we need to provide blood, providing oxygen, nutrients to the cells, and remove cell waste. And this is critical when we print such kind of structures. Again, we are developing different types of strategies to print vascular channels in our constructs. One example is printing sacrificial inks that will be later removed, creating the channels. So this is one example. We have a support bath material, a material that supports the printing process of the ink. We radiate, cross-link that support media, remove the sacrificial material, and by doing this, we create the vascular channels. The other approach is using coaxial extrusion, which allows us to print two different materials. Again, The inner material can be a sacrificial material removed after printing. But we can also print inks containing cells. So we can print one ink containing the endothelial cells to create a vascular system. Some challenges that we have, and one is related to shape fidelity. Inks are quite soft materials, so it is quite difficult to obtain very well-defined channels. This was something developed by an Eureka student quite recently in our lab. So she decided to use a silicon tube attached to the coaxial needle, and we irradiate the material when the material is moving through the silicon tube. And these allow us to obtain, by the end, tubular structures with well-defined geometrical characteristics. All of these strategies have one aim, and the aim is to be able to develop vascularized cell-laden constructs that will promote the integration of such structures once implanted into the body with the surrounding tissue. And with this, I finish my talk. I hope that I be able to answer the question, can we print cells directly into the body? The answer is yes, but we are in an early stage process. Thank you very much.
Hello. Yeah. So does anyone have questions for Prof?
Thank you. In one of the earlier slides, you mentioned using machine learning to do some kind of simulation instead of doing like the physical experiment. Could you go into more detail on that?
Yeah. So basically this. So designing the right scaffold is critical for us. Designing and validation, it's time-consuming and expansion. Before putting the product in the market, we need to do preclinical studies requiring lots of animals. So basically, we are using machine learning to address this. So we use histological images, typical till 120 days, of scaffolds comprising different architectures and different material compositions, training the system in order to be able to understand if we change the architecture of the scaffold, if we change the composition of the scaffold in terms of materials, what will be the long-term performance of the scaffold without doing animal studies. Because right now, we are designing scaffolds for what I call it as T0. We are not designing the scaffolds for T0 considering Tn. And this is what we want to do using artificial intelligence, is to design the scaffold for today, considering the performance in 1 year time.
Thank you.
Any more questions?
Hi, Prof. Paulo. Yeah, so I'm interested in the plasma treatment of the specific structure you mentioned, right? So could you explain more, how did you do that? Because the effect of the plasma treatment usually doesn't last long before you grow the cells, right? So how did you do that?
No, but I didn't mention that. In all cases, it was necessary to do a process optimization. So we consider different things. So we considered, for example, the distance between the plasma unit and the scaffold. We consider the effect of the velocity used to move the plasma system. So all of these parameters were taken into consideration in terms of durability of the effect and in terms of the effect itself.
Okay, okay, thanks.
Hi, Prof. Thank you for the talk. My question is mainly regarding how do you keep the whole system or whole printing sterile? Like,
Yeah, so what we are doing right now, and Yufei is there, and she's part of the team, is so we are renovating a space at the Singapore Center for 3D Printing, and we have two main areas. So one is an area dedicated to material preparation, an area where we will have some machines to print the scaffolds, and a closed area related to bioprinting, where we have a cabinet with controlled conditions, and we have the bioreactors there. So yeah, everything under controlled conditions.
so for the scaffold itself, does it have antimicrobial coatings or?
No, it depends. So you can incorporate, for example, silver particles. I didn't show, but we had a project with a company from UK called Matoka, where we use synthetic anneal to create electrospoon meshes with antibacterial properties. So it depends on the application, but yes, we can.
Okay, thank you.
And after the fabrication, by the way, we sterilize the scaffolds, so the scaffolds are sterilized.
Okay, good afternoon, Prof. Paulo. So I have two just technical questions for one each, scaffold printing and also cell printing. First of all, for the scaffold printing, just now I recall you present a work on the dual material system, which I think, if I recall correct, is mainly on the bone cancer system using different ROS. My question is that because these two materials are in close proximity, and especially inside implant the bone, do you have any mechanism to prevent actually the diffusion between this graphene oxide? Because so that these two dual material that don't become one, so that they still serve their purpose. Second question regarding on the cell printing, because so far I think your slide was a bit brief, just mentioned the cell and the bio ink. I just wonder, in the bio ink, is there any criteria or any what the additive you add in, such as hormone, growth factor, or in it, even antibacterial? If there is, may you share your expertise or your insights on the selection? Thank you.
Yeah. Okay. So starting from the first question, the graphene or carbon nanotubes are mixed with a degradable polymer. Even for this outside layer, the levels are relatively small. So I think that the maximum that we used for this outside layer was 5% by weight of graphene or graphene oxide. So very small quantities that are released natural from the body. So there is no mix issues. So the polymer is degradable, and these materials are small quantities. The second, yeah, the design of the ink is much more complex than I mentioned here. So considering, for example, the pectin. First, we need to guarantee that the gel presents bioactive cues. So you can see here that we decorate the scaffold with these RGDs. Another thing that we need to control is the stiffness of the gel, because the stiffness of the gel has an impact on how cells grow inside, how cells differentiate. So there are different parameters that we need to consider when we design the scaffold. But tailoring the properties, decorating these with bioactive molecules, adding growth factors, degradable peptides, this is part of the ingredients that we use when we design these inks.
Thank you for the sharing.
Oh, hello. Hi. I want to say thank you for this very interesting talk. I was just curious, you've mentioned that printing cells is in the early stages. According to your predictions, how long do you think it will take us to print fully functional organs?
Okay. So I think that it was in 2007, I participated in a meeting in Washington at NSF, and the meeting was about tissue engineering. And by the end of in the last day, after lots of discussions, NSF asked us, okay, give us an idea about one organ and when can this organ be printed. And I don't remember exactly the reason, but everybody mentioned, okay, this was, I think, 2007. By 2020, we'll be able to print a liver. We are still not able to print a liver. There are very interesting steps. So one of the major limitations that we faced was the amount of cells that we need to create an organ. I was impressed with companies working on food printing. Recently, I had a meeting with a company from Israel, and they told me about the bioreactors that they have. So this amount of cells is no longer a problem, apparently. Now, the problem that we have is more technological. So tissues are complex, hierarchical, multi-material, properties changing, and from a printing process, we still don't have such capabilities. So we started by using electrospinning and extrusion to create some kind of dual-scale structures, but tissues are much more complex. So besides potential cells, materials, essentially we have problems associated with the printing technology.
Great talk.
Thank you.
Really enjoyed it. I actually have a question kind of following on with that is how would you say the scaling up process of printing will look like in the next 20, 30 years? Say we solve all the technological problems with printing, but I recall one of your slides says something like 2 million Syrian refugees had bone damage, right? How would you deploy I guess this technology to kind of reach the masses? I just interested in your thoughts.
So bone, cartilage, skin, no major challenge. And they are relatively simple tissues. What I'm expecting to be, not in 20 years, I'm expecting to be able, sooner than that, is to add a couple of slides related to pancreas. We are starting a project with colleagues from an A-STAR institute focusing on creating pancreatic models. So again, we need to develop new printing strategies, materials, vascularization is critical. So this is something that I believe in a relatively short period of time I will be able to show. And again, that's why I mentioned that my presentation is a kind of journey, because step by step we are increasing the level of complexity. And I'm an optimistic by nature, so I think that even during my lifetime, we'll be able to see this 3D printing to print much more complex tissues directly into our body.
Yeah, I really like your talk.
Thank you.
It's great to see you have so many interesting ideas that was working so well. I'm particularly interested in the idea that printing cells into the body. But one thing I'm not clear is, compared to printing the cells directly into the body, another way is you do the printing outside, then you transplant what you're printing into the body. What is the unique advantage of printing directly into the cells into the body?
So, I don't know if you heard about a new additive manufacturing technology based on volumetric polymerization. So it's a system containing a resin and creates objects very, very fast because instead of a spot polymerization, they irradiate an entire volume. We are considering such system to create cornea devices. And because the fabrication is very, very, very fast, this will allow us to have the machine near the patient, printing the cornea and implant it. So time is the major advantage. So we can print in the clinical theater and implant it, or we can print it in the clinical theater directly into the patient without printing, pre-culture, and implant it. Because that is not the natural process. What doctors do is an immediate intervention. So,
Agree. Yeah, thank you for the clarification. Now I'm much more convinced. Another question on the same topic is, it looks like from the examples that you show, the existing system that try to print cells into the body, it looks like require that you have enough space so that the nozzles can access to the resin, right? Which look like it really limit the application, so to only somewhere that very topical, right?
Yeah.
Yeah. Is there any way to, or you have some idea about to expand the application into conditions where you can print cells into somewhere that is not easily to access?
So this is a good example, cartilage. So in the case of cartilage, to print an osteochondral construct, we need to replicate this arthroplasty intervention. Well, we are discussing with a group from Technion in Israel. They have, I think that they call it as a kind of snake robotic system. So like cables with a kind of snake structure that can be controlled using different strategies, quite small. So we are developing the materials now, but this is what we are planning to do. So very small holes. We need to have one small hole to get an image of the defect zone, one small hole to print the material, one small hole to irradiate the material, if not possible to join the two operations together. So this is roughly what we envisage for cartilage.
That's exciting.
But the scale, yeah, we cannot print cartilage using a needle like this. Yeah.
Any more questions? Last question. Any more? No, right? Okay. Oh.
Hi, Prof. I would like to ask, do you anticipate this kind of technology can be used in to save the endangered animal, like saving their genes, then maybe impossibly like printing like their next generations, help them, yeah.
To do what, sorry?
Yeah, so like in saving endangered animal, in a sense, because I project this technology is very similar, like gene manipulations. Yeah, so maybe you can share your expertise on this area. Do you anticipate, like, yeah?
So during many years when I gave talks about biomanufacturing, I remember that I ended all the presentations with one slide. And the slide was a photo of my son. He was quite young on that time. And I finished my talks mentioning something like this. I'm fascinated with bioprinting. This is an amazing technology, but nothing compared to nature. So I think that this answers your question. Fascinating technology, but far from what nature is capable to do.
Okay, so due to time restrictions, so I'll stop the Q&A here. So please give another warm applause.
Thank you.